session. Our next speaker is Jiarui Fei, and he will speak on tensor multiplicity via upper cluster algebras.
So first I want to thank the organizer for giving me this precious opportunity. And also I want to give my special thanks to Joshua. I think he is a graduate student here. This morning I forgot to bring my notes, and he very nicely helped me to print this thing out. In the beginning, I want to first review some basic of simply connected Lie group. Yeah. So maybe the volume stops. Yeah, sure. Better? Wait. Okay.
Is that too much? Okay.
So, simply connected Lie group. And we know that the simply connected Lie group are classified by linking diagram. So I think good example to keep in mind is the type A. So let's say the type A R. The example is SL R plus 1. This is a good example to keep in mind. So the category of representation is very nice. So category of representation, very nice. They are N category, and the most important one is they are semi-simple. Representations is semi-simple. So that means each representation is going to be a direct sum of irreducibles. So the question is, what about irreducibles? Irreducible representations are parameterized by the codominant weights. So irreducible representations are parameterized by dominant. So dominant weights are let's denoted by P is equal to a positive sum, actually non-negative sum of fundamental weights. So I go to from 1 to R. So those fundamental weights are dual. Those are dual to the co-roots of this Lie group. So if you forgot what fundamental weight is or dominant weight, don't worry. So just take this as a positive vector, non-negative vector. So just treat this one as a, because I'm going to identify this one with a vector with coordinate like AIs. So just treat this one as a positive, non-negative vectors. Integral actually. So the category is also a tensor category, so you have two representations. I want to change here. Maybe I want to use lambda. So given two irreducibles, we can tensor together. So I get another representation. So it will decompose, because it's semi-simple, into irreducibles. But this is not quite right, because each irreducible might appear with multiplicity. So it might appear with some multiplicity. I denote by C, mu, and lambda. Well, this is the number I would be interested in. Well, in general, to compute this number is not easy. But if you go through the first course in the algebra, by the way, so the category of representation of simply connected Lie group is exactly the same of the corresponding Lie algebra. So if we go through those courses, you know that this number is a classical formula due to Stillbridge, which says, oh, this is a long formula. I can barely remember. I can show you here. this W and W prime going to be run through the Y group. So in type A case, those Y group are just symmetric group. And what about this? This is Constant's partition function. So somehow this one is somehow under control. It is computable. It's concrete. But in general, it's not very easy. But this is not the main problem. The main problem is here. It goes through two symmetric group. It's going to be double exponential. So this is I mean, if you go some big example, this is not reasonable to use this formula to compute. So, what about, is there any better way to compute? So in type A, the situation is nice because we know there's a little Richardson rule, which is much better than this. But even better thing is around 2000, Knudsen and Tao, they invent hive model. So they invent the hive model. So what is a hive model? Basically, for type A, basically they define a cone, and if you want to compute this coefficient, you just take a fiber polytope inside that cone, and this number just equal to the lattice point inside that cone. So that makes things very concrete and nice. And also because there's polynomial algorithm to count the lattice point, so it becomes polynomial algorithm. And also they use this model to prove some deep theory like saturation conjunction. So this makes things very nice. But the problem is outside type A, the situation is not much better. But there's also polytope, so something similar to hive model due to Bernstein and Zelinsky. They have model for all type. But those models are not as nice as hive models. So hive models have nice presentation, and the matrix, to describe these polytopes, you can use hyperplane presentations, and those hyperplanes can be easily computed. And their model, for let's say for type E, usually it's very hard to compute. So my goal is I'm going to generalize the hive model in some sense to all types, and those models will improve Bernstein and Zelinsky. Try to generalize. So this is our goal. Generalize a hive model. So now what's the idea? The idea is I'm going to construct a multi-graded algebra. So the algebra will be graded by the triple dominant weights, and the dimension of each graded component going to count those numbers. So now the question is, what is this multi-graded algebra? So the algebra I'm going to consider is I take the coordinate ring of G coordinate ring of G is the group. Then we take invariant, so U minus. In type A, this is the lower triangle matrix, the set of lower triangle matrices. So I take the invariance, and we know that this is the classical result. This is the model for G, which means this decomposed into a Dirac sum of irreducible G modulus. So which is this one. Well, I still like to use U. And each irreducible appears exactly once. So now I can tensor that one with another copy. And then I'm going to take invariant, which is a dual. So we have a G, but we have action of G on two sides. So we quotient out this U minus from the left, then I can quotient out the U, which is, for type A is the upper triangle matrices from the right. So this one gives you the dual. This one, dual. this one is equal to this. So now if I tend them together, you see this is just a direct sum of so this is a rule.
Can you change the pen?
Marker is very hard to read.
Oh, okay. Well, this not. I mean, now this one we're going to. This one going to be. Oh, this is much better. Now we want to extract this number, right? But the way to extract it is we take G invariant.
Could you say what the top line is?
Huh?
Could you say what the top line is? It's still
Top line. So the G invariant, take coordinate ring, then take U minus invariant. And this is the same topic. So this is U minus invariant. Then this one is take U invariant rather than the U minus invariant. And then take the whole thing, take the G invariant. Then this one becomes just like home, this representing and the other one. But they are irreducible, so they just become a cake, right? The vector space, one-dimensional vector. So in this way, I extract this number. And of course, this algebra is graded by triple dominant ways. You do that. All right. So let's denote this ring by A. So let me show you the big picture. So the picture is I'm going to show that this one is upper class algebra. So this is a graded upper class algebra. So this is the shorthand for upper class algebra. So of course, to find upper class algebra, you need to specify a quiver. So the quiver is, I'm not going to tell you what the quiver is, but we'll talk about it later. So this is the first one. They are isomorphic. And the class algebra, it turns out that I can parameterize a basis using the lattice points. To parameterize a basis. Of course, by lattice points, I mean lattice point inside some polytope or polynomial. So now, this is not quite enough because, I mean, the reason for the first step is this A is just algebra, right? But now it is equal to upper class algebra to have more structure. Yeah? Remember, the class algebra is combinatorially defined algebra, and it certainly have more structure. But the more structure is not enough, still not enough. The good thing is, there's an underlying representation category sits behind. The representation category going to be the representation of quiver with potential. So this one we're going to be categorized by this upper class algebra. Now originally, the lattice point is something bad. But with this one, it gets animated because the left point has meaning in the representation category. It is going to be the Gaussian D group of the homotopy category of corresponding Jacobian algebra. Now I'm going to explain those terminology later. And that is still quite not enough because we are not just showing that it's parameterized by a lattice point. We need to explicitly describe the polytope. So how to describe polytope? I need more. It turns out the quiver appeared here. This one is so-called arch quiver. It is almost equal to the Auslandreiten quiver of presentation of. So this quiver is kind of special. It's called arch quiver. So again, in the beginning, the quiver, the vertex is dead. But now it gets another meaning. The vertex of quiver begin to talk to each other. So that leads to, I can use the stability condition to describe a set of representations. Those representations are going to call it boundary modules. Boundary modules. I can use these boundary modules to describe the polytope. To describe the polytope. So how I describe it? So remember, so a polytope has something like this, right? It can have a lot of lattice points inside. So to describe a polytope, I use hyperplane representation. So that means I take a vector, I use row vectors always. So multiply by a matrix H. So this is going to be a matrix which encodes a hyperplane. So greater or equal to 0, and x possibly times another matrix equal to 0. So this is our description. So to describe it, I need to specify each row of H. Each row of this H is given by the sub-representation of those boundary modules. So this is the whole idea. Of course, basically, I think every arrow here is a theorem. But you don't treat it as a commutative diagram. It's just a sketch of ideas. But of course, it's not everyone is due to myself. This one is due to the work of Dixon, Weyman, and Zelinsky. And I said that given representation, I can find an element, and I can map two elements in the graded upper class algebra. So the map I use is so-called generic character, so generic character. So this map, due to several different people, I think the prototype of this one is due to Caderouet-Chapeton, and later, in the setting of Kuiper with potential for class variable is also due to Dixon, Weyman, Zelinsky. And in the setting of class category for upper class algebra. So upper class algebra is slightly different from class algebra. For basis, it's due to Blanc-Mondon. And in the setting of Kuiper with potential, it's due to myself. And the first one, by the way, this one is also considered by, different people. So notably, it's given by, considered by Forka-Gontarov. So Forka-Gontarov. So this arrow here, a partial and weaker result is also due to Forka-Gontarov. So what do I mean by partial? So I think the thing they consider is also for every singular Lie group, but I think they only show the case for type A. I'm going to tell you the weaker, the meaning weaker, maybe at the end of the talk. Okay, so the rest of the talk I'm going to explain everything briefly. So I think good to start. I'm going to start with from here. The reason is once I introduce this one, I can give you the main result immediately. So it's good to show a picture first. Whoa. I think everyone here understands this quiver, right? This is Auslander eigenquiver of type A3 quiver. So this is correspond to A3 quiver. And that is those injectives, simples, right? This is Auslander eigenquiver. And this quiver is related to class algebra. I think this first observed by, actually discovered by Fomin and Zelinsky, that the class algebra of this quiver is equal to the unipotent group. The coordinate of the U minus or this U is exactly the curve. Of course, they discovered that this is class structure here, and the observation is made related to this Auslander right-hand algebras given by Grice, Leclerc, and Schreier. But today, I'm going to consider something slightly different. I'm going to consider, instead of representation, I'm going to put presentations. So what is the presentations? This is just a morphism from one projective to another projective. So presentation from, let's say I use P, I like to use P plus to P minus. So this is the presentations. So for each representation, I can associate a presentation certainly given by the, just present its representations. But they are actually more, right? So I think in Professor Kaurigubi's lecture, he had something like Pi. This is the indecomposable ones corresponds to vertex I. So it goes to 0. So this one I would call a positive presentation. But then there's another one, for example, Pi goes to Pi. This is also, of course, identity, right? So I call it neutral ones. Neutral presentations. So remember, this is the one thrown away by Kaurigubi, right? But this one is valuable to us. So with all those objects, we need to put into our Ausland-Dryden quiver. So the thing we got is, let's just say for this example, what I got is P3 goes to 0, and P2 goes to 0, P1 goes to 0. And those ones also become frozen by definition. And on the bottom, I got 3. They're all frozen. Yeah. So each arrow here is irreducible morphisms, but the dashed line is also arrow. I just want to use the dashed line to distinguish from the morphism arrow. So those arrows are called translation arrows. All right. So given this quiver, I can describe the main result here. So remember, I want to describe this H and this sigma here, right? Both are matrix. So sigma is a matrix encodes weights. So it is well, each rows of sigma corresponds to a presentation P1 to P0 going to be a triple dominant weights. So let's say this presentation, I use F. Okay? So I put here going to be the F minus. I'm going to explain what F minus and F plus. So F minus is the multiplicity of this P1 in terms of indecomposables. Sorry, negative corresponds to this one, sorry, corresponds to P0. So this is the multiplicity correspond. I'm sorry, I still use positive and negative. Yeah, so this is the multiplicity of this P minus, and this is the multiplicity of P plus. And what about this one? This one. Oh, by the way, so multiplicity is a vector in where? It's a vector in Z to the power of R, right? The rank of the Lie group. So this is in ZR. This is also in ZR. But we're still missing one ingredient here. This one going to be a, this is denoted by F. this one going to correspond to a elementary factor. That is, everyone is 0 except for one place 1. So, so that number is determined by which one is the representation translates from. So for example, for this I2 translates from this one, right? Translates from this one. So I just put E2. So E2 is just 0, only 1 at second coordinates, and everywhere is 0. So that is our sigma matrix. Now what about this H matrix? So that is a key point. H matrix. So H matrix is related to the boundary module. So I'm not going to define boundary module in general, but I show you in this example. So each boundary for each further vertex, there is associated boundary module. So let's say take this one. I think it's good to change to another picture. So I only write down, let's say this P1 to P1, I just use 1, 1. So 1 corresponds to the multiplicity of the first one, and multiplicity, that which means P1 appeared once. P1 appeared once. Right. I use this P2, I change to so on. So the resolution of S2 is given by P3 to P2, so it is 2, 3. So this S1 is given by 1, 2, and so on. I get this one is 1, 3, and 3, 3. So for this one, you see, at the first coordinate, those ones have all coordinates labeled by 1. So I just take everywhere, I take a module which supported on those vertices. And dimension vector take exactly 1, because 1 appear once. So this is a representation, have dimension vector 1, 1, 1, 1 here. And similarly for this one, I got 1, 1, 1, because only those vertices have 2 appear. Right? And this is here, and also for these ones, you see it is 2 here. Yes, 2. So 2, 2, 2, 3, 3, 3, 3. And similar for this one, but this one is special because we don't have labels here, right? For somehow this we should keep in mind this is actually corresponds to this one somehow. So because this one, every one here is translated from here, so they have the same coordinate here. But this one is invisible in my labeling, right? But so for this part, I always take the straight lines. Straight line. So those are the boundary modules. Those are the boundary modules. So once I get boundary module, I take all the sub-representation of all the boundary modules. So this H corresponds to the sub-representations. So each row of H is the dimension vector of sub-representation of the boundary module. Okay, so several remarks. So first, as you can guess, this is for type A, you get all straight lines. But as you can guess, for other type, let's say type E, you not necessarily get straight lines. And also, the dimension vector of those boundary module can have greater than, dimension can be greater than 2. So because the projective resolution here can have multiplicity greater than 1. So somewhere maybe in the end, I will show you that the picture for, let's say, bigger examples. So the boundary module can become very complicated. Okay, the second remark is, what about the non-synchronous case? For non-synchronous case, I still have, of course, I need to change to the representation zero value equivalent. I still have this Ausland-Rider equivalent. Still have this one, but it will be a value equivalent as well, right? But we know we have class algebra of value equivalent. So everything still works, but I want to mention that in our main result, I'm sorry, I didn't mention in the beginning, that there are several arrows won't work in the synchronized case. I think it's good to let you. So for synchronized, for value quiver case, this arrow is not working. I mean, there's no machinery here. And of course, then this one not working, then here is the problem here. And this one is not isomorphism, but of course, conjecturally it's also isomorphism. But I can only prove like this, including. But the rest is okay. So we still have the description of polytope. Everything is working. All right, so finally, the third remark is about Knudsen-Taussig model. If you look at this type A case, the relations given by those boundary modules is different from Knudsen-Taussig descriptions, because if you're familiar with type model, the inequality is certain kind of Romney type inequality. Roughly speaking, you have a Romney here. You take the opposite vertices. The sum of those two numbers should be greater than the other two. So this is Romney type. So it looks slightly different, but it is known that you can do a unimodular. I think yesterday's talk, I think Lara also considered a unimodular transformation to make it exactly the same as Knudsen-Taussig model. Oh, thank you so much. Knudsen-Taussig model. Okay, now I want to finish the rest. So this part. I'm going to, this one's done. So I think the most important one is the middle one, the representation theory of quiver with potential. So I start with a quiver like this. I mean, I want to model the upper cluster or cluster algebra. I think the most important observation in Dr. Wimann's Zalevinsky's work is the underlying category to model the cluster algebra is not the quiver of this quiver, category of this quiver, rather than, it should be the category of quiver with potentials, right? Potential, roughly speaking, is just a linear combination of cycles. So for this one, I need to put what kind of cycles. So cycle, it's very little choice. You just take each little small triangles. Each one is oriented cycle. You just sum up these two together. So this is the potential we're going to put. And I think this recipe also works for all type. And you always get a rigid potential. So quiver with potential. So W is going to be just sum of small triangle. I'm not going to use precise words here. Is this going to small triangles? Now, once we put the potential, we can associate the Jacobian algebra. So Jacobian algebra of this quiver. The quiver usually using this delta. So delta W. Well, I'm not going to define Jacobian algebra. Basically, if you have a potential, you can use the cyclic derivative to derive a set of relations. And these relations will generate an ideal. So the Jacobian algebra is the quotient algebra of this k delta by these relations. So we can just treat this Jacobian algebra as certain quiver with a relation which is derived from this W. Okay.
Sorry, can I just ask, how are you treating the arrows between the first vertices here?
Yeah, that's good. So those are the frozen ones, right? I still put potential here. The arrow here, I won't delete it. I keep it.
But you impose the relation coming from it or not?
Huh?
You impose the relation.
I impose it as well. Yes. And by the way, here this one, there's no translation in the bottom. So with this construction, I can finish the category with the CC character, the alpha arrow here. So given a G vector, so I'm going to tell you what the G vector is. The G vector basically is the weight vector of a presentation in the category of representation of Jacobians. So those are the elements in the Gaussian group of homotopy category. Well, almost how to use the notation category of the Jacobian algebra. Potential. This is element there. So, so this is integral vector. Given G vector, I can associate. Given the G vector G, I can decompose it into a G plus minus G minus. So those one is similar to the situation here. This is going to be the multiplicity of our presentations. So I can associate this G of presentation. So P G minus goes to P G plus. Well, still I mean plus. So now I can get because you know the homomorphism between these two spaces is a fine space, right? So I can take a generic morphism there. So we'll take F generic. So take F here. F is generic in the space of presentations. Then I can get a co-kernel. I denote by co-kernel of T. Then I can have the formula now. So the cluster character CW maps this G into following formula. So that is xg. So remember, this x is a set of variables attached to each vertices. So it's x to the power of g. I'll take all the characteristics of this Grassmannian of this co-kernel of G, and then multiply by some variables. So that is x to negative e. Well, I haven't introduced the B matrix, but well, let's just use another variable. Let's say y to the power of. So y is a variable which can be translated by a monomial translation to from this x variable. So you don't really need to know it. The key point is from this formula we have a leading term x to the power of g. So this is elements in the upper class algebra. This is elements in the upper class algebra. This is. Yeah, so we have a leading term with power of g. So the point is now the last point we're going to be just we're going to just take this g back. So the g will correspond to the last point. Okay, so now let's try to summarize it. So we have this class character map CW, and I take the span of this class character map, and this one goes inside the upper class algebra of this Kribbe with potential. So did I use this notation before? Yeah, so delta Q delta 2, and the potential here is this one. So this one goes to upper class algebra, and we know that it's easy to prove, relatively easy to prove. This one is lying the algebra we considered in the beginning, which is A. So if I want those G vector parameterize bases, certainly we need another direction. So I want this one. I think this is relatively hard to prove. I'm not going to detail. But anyway, so in the end, the result is everything is equal. Everything. So I want to go through some technical detail a little bit. So I think maybe it's good to define the upper class algebra. Do I have time? 8 minutes. Yeah. So I think it's good to start with Laurent phenomenon. Which is already appearing in the last lecture. So any elements in the cluster algebra can be written as a Laurent polynomial in any cluster. In any cluster. So any. I'm not going to write it down. So cluster algebra of this delta is lies inside the Laurent polynomial of each cluster, which is mutation equivalent to the initial ones. So, I mean, delta x prime, delta x prime. So this is a rephrasing of Laurent phenomenon. So cluster algebra lies in the intersection of all possible Laurent polynomial in clusters. So by definition, this one is equal to the upper class algebra. This one is equal to the upper class. This is the original definition of Fomin-Salinsky. But here I'm going to consider a slightly different version of this upper class algebra. So I'm going to still I'm inside this Laurent polynomial in all clusters, but for the frozen ones, I require it to be polynomial. So I won't allow it to be a Laurent polynomial. So it should be polynomial in the frozen plus variable corresponds to the frozens. So now I want this the first arrow work, the TC formula work. I'm unable to take all possible G vectors. So the formula here, I'm not going to restrict all possible G vectors. I need to consider a special set. So the G vector corresponds to the G vector. We're going to consider the so-called mu supported G vectors. So what does it mean? That means if I take the co-kernel of the representation here, this representation should not be supported on this frozen vertices. So the representation, which means the co-kernel of G is not supported on frozens. And this is exactly the condition to describe the polytope. So I think how to characterize a representation is not supported on certain vertices. So it's just given by I write it here. So it's given by the homomorphism of this representation with the vertex we want, which I take injectives. So the representation M or a certain injective representation, this one going to be 0. But on the other hand, for those injectives, we always have vanish of shifted homomorphisms. Or shifted is also 0. So roughly speaking, combined, these conditions give rise to certain stability conditions. So using the stability condition, in the sense of king, right? So that is how those sub-representation going to arise in the description. And of course, the boundary module is not I. Yeah, you certainly can take I, the injectives. But the problem is usually if you take the injectives, you get lots of relation, which can be redundant. So I think that the one is the algorithm in my paper is that I can have algorithm to derive a better relation using, I can derive algorithm to compute this boundary module, which gave a better relation. All right. So, well, it's good to now I'm going to talk about what's the Fock-Gantarov result. For Fock-Gantarov, I mentioned that the result is slightly weaker. What they consider is, remember, this algebra A, the algebra A is this. So they consider, of course, G invariance. So they consider, like this one, like geometric objects. So this is, each one is a modular space. You product three modular space and quotient on the G. You get a, you get a modular stack. So each point here is so-called a fine flag, or base affine flag. So if three flag here is in generic position. So which means, of course, you take a stack, you take a generic part, it happens to be a variety. So the generic part of this, so let's say, let's think this one as a stack. This one corresponds to a stack, which I denote by A. So A is a module that corresponds to each one. So A cross a dual modulo G. This is the modular stack. The generic part is a variety. So now the question is, what is generic part? It turns out, if I translate their result, they prove that the generic part is a cluster variety. So if I translate their result into algebra big language, which says the upper class algebra here, with localizing at all frozen vertices, going to be equal to this A, localizing at each frozen vertices. So this is slightly weaker than the result here. Well, yes. So I think the good point is, so for our description of polytope and quivers, those delta Q2 is uniform, right? For each quiver, you associate this AR quiver of presentation, and all the description of boundary modules are also uniform. So the question now finally is, can you compute sub-representation effectively? Actually, everything, I think, except for E7 and E8 can be done by human being. For E7 and E8, I have algorithm using computers. So you have uniform description, then you have algorithm. So everything is set for. So finally, I will show you slides, which I think is certainly not satisfied with the case of case of type A. And see, in type G2, this is a valued quiver. And some place you see there is a superscript. The superscript denotes the multiplicity of the projectives appearing in the resolution. And for E6, you have even more bigger quiver. And if you look at this one, which one? If I look at the boundary module corresponds to these vertices, it is rather complicated. You pick everywhere where 2 appears, right? You have a lot of spots, right? Rather than straight line, you have a lot of 2 appear. And somewhere here, you see the multiplicity also appears 2, right? You have these boundary modules, and then I think this is the maximum ability I can do. I can write down the submodule for this one, but for E7, E8, you can guess. I can do that. All right, that's the end of my talk.
Thank you very much. Are there any questions? Yes.
Yeah, for other types, the saturation property for tensor products fails. Can you see that from this picture?
Yes. So fails. So for example, for type B4, well, I'm not going to exact ones. I'm going to just show you something like 0, 1, 0, 1, 0, 0, 0, 0, 1, well, 0. Make another 0 here. So this one, if you add these weights together, you get something like 2, 2, 2, 0. And what is the G vector corresponds to it? That is, I mean, this is each G vector corresponds to certain vertices. So this is like E. Those are just like 3 individual ones, and you got 2 to 2, but now, you know, you can't do. You can't fail. All right. Yes, please.
Your examples that the Tensor was actually equal.
Oh, very good question. So, for all except type A fail, they have a gap. The upper class algebra strictly greater than the cluster one. For type A, still open. I verified up to n equal to 6. They are all equal. And I hope it is, well, I'm not sure. This is something I don't know. It is always equal.
I see no further questions. We're going to meet again in 7 minutes at 11:20. Let's thank the speaker again.